Hello, and welcome to our capstone demo video. My name is Alton Olson, and my teammates are Deanyone Su and Chen. For our capstone project, we decided to build multiplayer Tetris on an FPGA. For those not familiar, an FPGA is a type of chip. It stands for Field Programmable Gate Array. Inside an FPGA is a sea of logic gates. These gates each can do very simple computations, like AND, or not, and you can link them together to do more complex calculations, like adding two numbers together. Because there's this sea of gates, you can link together different gates independently to do these calculations in parallel. The main alternative to using an FPGA would be to use a microcontroller, a tiny computer chip. Microcontrollers also have a lot of logic gates, but they are pre-configured and you can't link them together in different ways. Instead, you write a series of instructions that are executed one at a time, in order. Most programs and most games are written this way. We chose not to use a microcontroller and to instead use an FPGA because of the added challenge and the advantages of the aforementioned parallel calculations. Our two main goals for this project were 1. To capture all of the Tetris mechanics accurately, and 2. To have frame-perfect inputs. Frame-perfect inputs are the gold standard of input latency for any game. They're defined as having your input show up on screen by the next frame. Since our game runs at 60 frames per second, a less than 1 frame delay between you inputting something and it showing up on the screen is nearly imperceptible, and it feels like your inputs are happening instantaneously. Since we were going through all the trouble of creating this game on an FPGA, we wanted to really capitalize on its advantages. Our complete solution consists of 2 FPGA boards, 2 custom-made controllers, 2 off-the-shelf VGA monitors, and 2 custom auxiliary boards for connecting the FPGA to the controllers, the audio module, and each other. We designed the system with 2 of each component because we wanted to build 2 independent game consoles with the feature of being able to connect together. If the 2 pieces were going to be inseparable, doing networking between boards seemed pointless, as we could just do everything on one FPGA. More importantly, this is how real game consoles generally work. The auxiliary board has 3 connectors. The big 40-pin connector goes to the FPGA. The 2 smaller 16-pin connectors go to the controller and to the other auxiliary board. The chip is a digital to analog converter that converts the music data from the FPGA into a sound signal, which is then outputted on the audio jack. Here's an early demo of sound from when we were first prototyping with the digital to analog converter. Each controller is a laser-cut wooden box with 8 arcade-style push buttons. It has a 16-pin port that allows it to interface with the auxiliary board. This port is actually bidirectional, so we designed it so that reversing the cable would reverse the controls for left-handed players. In right-handed mode, the right hand controls translation and dropping of the pieces. You can see that I'm using the right-handed buttons here to manipulate the piece. When I flip the connector around, though, the hands switch. So now in left-handed mode, the left hand controls translation and dropping of the piece, and the right hand controls rotation. The actual game has 2 modes, Sprint and Battle. Sprint is the single-player mode, where you race to clear 40 lines as fast as possible. Here I'm playing Sprint mode. As you can see, there's no data on the right of the opponent's board because we're in single-player mode. The controller is intuitive and easy to use. It mimics the typical keyboard layout you might see when playing Tetris on the computer. Even for me, someone who's not very good at Tetris, it was easy to pick up and become familiar with. The queue of next pieces is generated by a random algorithm called the 7 bag. This is described in the official Tetris specification. There are 7 possible piece shapes: the I, J, L, O, S, T, and Z. Each time the queue is generated, the game picks a random permutation of these 7 pieces. This guarantees that the player doesn't get stuck with many undesirable pieces in a row, and also that the distribution of pieces is equal. To make sure that our game followed the official Tetris guidelines, we had to make sure that we adhered to many corner cases. One of these such cases is handling these moves called T-spins. A T-spin is when you spin a T piece through other pieces in order to rotate it into place. It's important not only that the game executes the T-spin correctly, but also that it recognizes that it is actually a T-spin. If you notice, whenever I execute the T-spin, the border of the game turns blue. It's important that we recognize this because executing a T-spin gives a bonus to the player in competitive mode and allows them to send extra lines to the opponent.
For multiplayer gameplay, we designed our own network protocol called T-spin, the Tetris Synchronous Parallel Interface, to send data between boards. In a 2-player game, a certain amount of information needs to be sent back and forth every frame. Each player should be able to see the other player's playfield, queue of pieces, and so on, updating in real time. There is also a garbage mechanic, where the lines you clear show up on your opponent's board to make things difficult for them. All of this data is encoded into a set of bits, or zeros and ones, which we divide up and transmit across a few wires several times per frame. A full set of encoded data is called a packet. You can think of each wire as a signal that can be either low or high at any given time, so 0 or 1. That signal is sampled at set intervals to get a stream of bits, which we can interpret as our data. T-spin is a 4-bit parallel stop-and-wait protocol with dedicated handshaking wires. This means a few things. We send data across 4 wires at once to speed up transmission, and handshaking is essentially extra communication between boards, letting the other know that a packet was received or that the game is starting or ending. Each packet begins with what's called a sync word, a pre-established pattern of bits that indicates the start of a data packet so that the receiver can distinguish a packet from just noise. When the full packet is received, an acknowledgement is sent back to the sender. This is what's known as stop and wait. You send a packet, wait for acknowledgement, and then send the next packet. If no acknowledgement is received, the packet must be resent after a certain period of time. To avoid duplicates, both the sender and receiver track what's known as a sequence number. This number is also encoded into the data packet and compared with the internal one so you can tell when a packet is duplicated. This is all important for reliability, as data can easily get corrupted or lost during transmission. Of primary concern to us is a phenomenon known as crosstalk, where electromagnetic interference between wires affects the signal. We have to carefully select where each wire is placed to try and mitigate this issue.
Modern Tetris uses a rotation system known as the super rotation system, or SRS, to determine how pieces should rotate between orientations. Each piece has 4 orientations: spawning orientation, left, right, and 2, which means rotated twice. SRS also defines a set of wall kicks which enable pieces to be rotated even in some situations where the resulting location for the piece, if rotated naively, would be blocked. Let's consider a situation where a piece is unable to be rotated in the direction specified. Say you have an I tetramino vertically oriented up against a wall, and you try to rotate it. If you rotate it without shifting the piece as well, then the piece would then phase into the wall, which is an invalid position. Instead, the piece is shifted as it rotates, so it lands in a valid position on the playfield. But where to shift this piece? This is done by checking a set of wall kicks. Each tetramino has a set of 5 shifts, which is called its wall kick data. Each time a piece is rotated, the 5 wall kicks are checked sequentially, in order of priority, to determine the correct placement for the piece after being rotated. If all 5 kicks result in an invalid placement, then the piece doesn't move and the rotation fails. This enables pieces to be rotated in nearly all situations that one might encounter in a typical game of Tetris.
Last but not least, we'd like to thank Professor Bill Nace, Jens Ertman, and Hailang Liou, and the rest of the 18500 staff for all their help this semester.